Welcome everyone to the colloquium this week. I'm very happy to have here Professor Stefan Soldner-Rembold, who is visiting for these 2 weeks due to the Dark Matter and Neutrino School, and he graciously agreed to give the colloquium this week. He got his PhD from the Technical University in Munich in Germany, and he was associated to the University of Freiburg, and he's currently the head of the particle physics group at the University of Manchester. He's a member of the DUNE collaboration, also of the SBND and MicroBoon collaborations. He's a founding member of the ICTP Gen 2 collaboration, and is involved in the building of the Pingu array at the South Pole. In the past, he's been the spokesperson of the D0 experiment at Fermilab, where he worked on Higgs boson searches. He's also a member of the NEMO3 and SuperNEMO collaboration, looking for neutrinoless double beta decay. And he's part of the HIPAP advisory panel, fellow of the Institute of Physics and American Physical Society. And earlier, he's had also some connections with CERN and DESI at the OPAL and ZEUS experiments, respectively. And today, he's going to tell us about DUNE, an international neutrino observatory.
Three? Yeah. Thank you for the very nice introduction, and thanks for inviting me to give a presentation here. Now I lost the technology on DUNE and giving me the opportunity to tell you about that. Let me just check it out. Yeah, it works. I haven't heard my name pronounced correctly for a long time. That was really impressive. It's usually. I usually have to apologize for the long name, but obviously not in Brazil. So I'll talk about DUNE, and I know that some of you have been, or the majority probably have been in the summer school, and they know everything already about neutrinos, but some of you are also not in the summer school, so I'll give a introduction which will tell you what Andre told you in several lectures. You know, like an experimentalist, we can compress this to 5 minutes or something like that. All you ever wanted to know about neutrinos. And then I'll talk about DUNE and the DUNE project, but to just introduce overall what it is, I'll actually be talking about. Is this laser working? Yeah. So this is DUNE in a nutshell. DUNE is the Deep Underground Neutrino Experiment. It's a next generation worldwide global neutrino project, which consists of what we call far detector in South Dakota, in a mine about 1 mile underground, consisting of 40 kilotons of liquid argon. That's a lot of liquid argon. Then it's called a far detector because there's also a near detector. There's a near detector that's here at Fermilab, and just close to where the neutrinos are produced, and that's the third component, a high power wideband neutrino beam. The physics flagship topics, and I'll talk a little bit about at least the first two of this experiment, are to discover CP violation in the neutrino sector, to see, observe supernova neutrinos, and also to contribute to finding baryon number violation, for example, proton decay. So this is where it goes. This is for those of you don't know where it is. This is Illinois, this is Chicago, and this is South Dakota. So the beam goes just through the big plains. DUNE in its current form was formed in 2015, so it's a relatively young collaboration. There have been predecessors of DUNE called LBNA and LBNO, both mainly in Europe and the United States. This is the founding collaboration meeting and that was in April 2015 at Fermila. Since then, we have come a long way. DUNE is a truly global project, and I don't know whether it's good whether I stand here if it records, but I should probably come closer. That's the problem, yeah? But it's a very steep angle point. Not complaining, just a bit complaining. So it's a truly global experiment, and it has now over 1,100 collaborators from 178 institutions in 32 countries. And the 32 countries are listed here, and I've highlighted a few. Of course, Brazil, obviously, because not only we are in Brazil, but because Brazil is an important, very important collaborator on DUNE. Then CERN, well, first because it's not a country, but particle physicists actually count CERN as a country, and it's an important collaborator too. The United Kingdom, because it's an important collaborator and because I am actually from the United Kingdom. And the United States, that is the host laboratory. This gives you just the breakdown of these members, about half faculty, but there are also already many postdocs, engineers, and PhD students. We are currently growing at a rate of about 100 collaborators a year, and we expect to plateau something like 1,500. It's the biggest neutrino experiment ever attempted. It's still about a factor 2 smaller than one of the LHC collaborations, but it's already a pretty big project. Why are neutrinos so interesting? Because they are a potential key to new physics. If you look at the standard model of particle physics and you draw the generations and the fundamental particles like this, as we know with the 3 families, and here are the gauge bosons. And you then use the animals as, so the mass of the animal is corresponding to the mass of the particle they represent. So you go from the blue whale here somewhere for the W and the top to, like the up is a duck, and then you see the neutrinos, and the neutrinos are really very light, and actually that's a bit out of date. We know the tau neutrino is lighter than this, but anyway, it's like an insect. Now that is very strange, and there's another strange thing about neutrinos, that neutrinos are always left-handed, antineutrinos right-handed, which is specific to neutrinos, and both points to something which could be physics beyond the standard model, saying that the Higgs boson, which we know is normally responsible for the mass of fundamental particles, might not directly be, indirectly yes, but not directly contribute to the generation of neutrino mass, and that the fact that neutrinos are so light is actually a reflection of the fact that there might be right-handed neutrinos at a much higher mass scale, and when you diagonalize the corresponding matrices, you get something like this, what we call seesaw formula, where the neutrino masses we observe is just the typical Dirac masses of 1 GeV divided by some very, very large scale. That's why they are so small, but that's why also neutrinos could point us to something which is happening at much, much higher scales. So what else is interesting about neutrinos? What do we know? What do we not know? So this is the neutrino mass hierarchy, and this was on the board just a few minutes ago. Somebody took it off. It was here from the previous lecture. And so I can skip over this quickly. We know that there are 3 neutrino types. We call them flavors. We also know that they have mass. We know that from oscillations. But we also know that the mass eigenstates and the flavor eigenstates are not the same, and you need a rotation to go from one to the other. We also know the splitting of the masses. That was also somewhere on the board. And so we don't know, however, how the splittings are arranged, whether it's what we call normal or inverted hierarchy. So how the 2 splittings are arranged. And we also don't know what is the scale of this plot. we only have an upper limit on the neutrino mass. We know the differences, but we don't know what's the mass scale. And we also don't know whether neutrinos and antineutrinos are actually two distinct objects, which would make them Dirac particles, or whether they are the same object, would make them Majorana particles. We also don't know whether there is CP violation in the neutrino sector, which means do neutrinos and antineutrinos behave differently. There's a slight contradiction in what I just said, but you can ask Andre about that. There's an answer to this. So that's how you get from from the flavor states to the mass eigenstates with this rotation matrix, which is called the PMNS matrix, which is like in the quark sector, the CKM matrix, generally a complex rotation type matrix. Neutrino oscillations are written like this. So your probability, the amplitude that a nu mu, for example, goes to a nu e is proportional to this term, which you can calculate. It's actually not that hard. There are these mixing angles. This is just for two neutrino flavors, so there's just one angle. When you have two neutrinos, it's a 2 by 2 matrix. And then this term here, if you write it out, it's just units. And then you get in the oscillation term here, this is the frequency. And you see the frequency is delta m squared times the length the neutrinos travel divided by their energy. And that's parameters we can play with when we look at neutrino oscillations. We turn on a third flavor, so this would be a mu neutrino beam, and you see it oscillate. Oops. When we turn, you get oscillations into the third flavor. And of course, it becomes more complicated because it's 3 by 3 and so on. One thing I should also mention, I don't know whether that was in lectures, when you go from vacuum to matter, things become more complicated because electron neutrinos, matter is, interacts differently with electron neutrinos than with muon tau, and that complicates the pictures, and that's called the MSW effect. So there we go. So what do we want to get at with DUNE is CP violation, and CP violation, when do I have to stop, by the way? When you say stop, or? Okay, good. Good, good. Yeah, just give me if I'm too long, just stop me. Good. So this is this matrix again, which we have now parametrized in terms of mixing angles. And then you see there is this complex phase here. And the complex phase is crucial to CP violation because CP violation, where C stands for charge parity and P for parity, then can only happen in if this object, if this matrix is complex. So if we have CP violation, which sometimes colloquially we call difference between matter and antimatter, then this angle delta, which parameterizes that, has to be non-trivial, so it shouldn't be 0 or pi. So this doesn't become real. Now, often, as I said, we talk about this in terms of it explains the matter-antimatter symmetry of the universe. We have seen CP violation before in the quark sector. We know that's not enough, so we need other sources of CP violation in addition to that. And there are theories out there that are called leptogenesis that say that the fact that we have a matter-dominated universe is actually due to the fact that related to the CP violation in neutrinos. Now, one has to be a little bit careful here because one thing sometimes people don't add is that this leptogenesis happens at a very large scale in the early phase of the universe, and what we look at is a low-scale CP violation. So you still have to, even if we discover it, you have to have a theory that brings us from, connects these scales. But it still would be a very, very important step towards that. And Andre is nodding. So I now see you there. Whenever I say something wrong, then good. Okay. Get the theoretical approval. I think that's basically what you learned over the last 2 days, roughly. Yeah. Good. Now, how do we get that? Well, the two neutrino oscillation formula is a little simple, and that's why you can derive it, and that's what you do in lectures. If you get the whole three neutrino picture in there, it looks much more complicated. And this is what you get, all these different, so this is the amplitude for nu mu to nu e, you get all these terms here. So let's just point out a few things, because that's what we actually want to measure. So we want to get to that phase delta Cp. But in order to do that, we have the dependence on all these other factors in there. A couple of things to note is that all of these are proportional to this one mixing angle theta 1,3. If that would be 0, we had a problem, and we couldn't do this experiment. Now, lucky as we are, it turned out that theta 1,3 is actually relatively large, which makes, and this was measured in reactor experiments over the last years, so that made suddenly, this kind of physics possible, because you could actually measure this because these terms are large enough, okay? As simple as that. So what do you do actually to perform the measurement? So you take a neutrino beam that's shown here with energies of 1 to 10 GeV. A neutrino beam is almost never monochromatic because it's very hard to, you get it from decays, so they are in a range of energies. And then you see, so this is the neutrinos we create, and then you see the different colored curves which are for different parameters, and here specifically important is the variation of the delta Cp. And now, after traveling 1,000 miles to the Rocky Mountains, this neutrino beam spectrum is modified by these curves. And that's what you actually measure. And from that, you derive your parameter delta Cp. So how do you build such an experiment? That depends on your baseline, where you start with the neutrinos, where the neutrinos end. Now, there are two fundamental baselines in neutrino physics. One is 200 kilometers, and the other one is 1,000 kilometers. Why are these fundamental? Because 200 kilometers is the width of the island of Japan. And 1,000 kilometers is the distance, basically, from Chicago to the Rocky Mountains, where they have mines. Yeah? Now, if you want to build a neutrino experiment over a baseline of 200 kilometers, you go to your formula, and if you remember what I showed you before, so this is the term, the oscillation frequency, and that we want to maximize. It should be pi over 2. And so if you put that in, your neutrino energy has to be low. If you go to 1,000 kilometers, because it's just a ratio, it has to be about 4 times bigger, yeah? Or 5 times. That's why if you want to build a long baseline experiment of 1,000 kilometers, you need a higher neutrino energy beam. And that defines, to some extent, the choice of technology. Because if you go to a lower baseline, you have lower neutrino energies, you are fine with building a water Cherenkov detector. However, if you go to larger baselines, you actually want to get your oscillation parameters and delta from fitting the whole energy spectrum in high energies, so you have to reconstruct the energy, and that's better with a liquid argon detector. That's the reason. You also have other issues like more matter effects, less matter effects, and so. But let's go on because time is running. So this is a movie that shows you what LBNF and DUNE is, and it comes on. So here, this is just, we start out, I'll just talk over her, yeah? You probably can't even hear that. So this is Fermilab, close to Chicago, prairie, restored land, really nice, surrounded by urban sprawl, so it doesn't, quite an interesting environment. This is the beam you produce there at Fermilab, and of course you can make neutrinos directly. You start with a proton beam, you accelerate the protons, then you have various pre-accelerators, then you hit with these protons, which have the order 80 or 120 GeV, a target, you create pions. The pions decay into muons and neutrinos, and there's your beam. Of course, it's not monochromatic because it comes, or with single energies, that's what we mean with monochromatic, because it comes from these decays. It goes slightly underground. There's a near detector, and then it goes through the Earth, and there is no tunnel there. The journalists always ask, where is the tunnel? It goes underground. A supernova happens right in time, as ordered. These are the liquid argon detectors. They are big. We come back to that. And then the neutrinos once in a while interact. And there it is. There we go. And that's a neutrino interaction. And then the data is read out. These are zeros and ones. This is for the public, yeah? I'm sorry. And then it goes to Brazil.
Like planet.
And then we'll figure out why matter exists. That's what they say in this. Of course, we don't figure out why matter exists, but that's you know, we are. But it's still is very fundamental. So my pacing probably screws up the whole filming. Anyway, so this is what I already told you. You make the pions. The problem with neutrinos, you can't focus them. They have no charge. So in order to do that, you have to focus the pions. You do this with horns, as invented by Simon van der Meer a long time ago. These magnetic horns focus the pion beam, and then from that, you get a focused neutrino beam, and you can actually choose the energy if you want a neutrino beam by going at different angles, because the energy of the beam depends on angles. But here we want a wideband neutrino beam. The beam, by the way, sometimes people ask, is much wider than, for example, the detector. Yeah? I haven't even never calculated, but probably kilometer wide or whatever. Would be a nice problem for a student to calculate. How wide is the beam? Do you know? No. Yeah, it's kilometers. So anyway, the width of the beam is much wider than the detectors. This is the beam spectrum, and the problem with building a neutrino experiment is that neutrinos don't actually do very much, which is pretty boring in a way, and they just go through us, they don't do it. So in order to measure neutrinos, you have to have a lot of them. You need a huge detector, which is why water is so nice, because water is cheap. Liquid argon is also pretty cheap. Liquid argon is $1, a US dollar a liter. That's actually not so bad. You need a big detector, and of course having an intense neutrino beam is part of this, and that's what Fermilab is working on. And I will not talk about this in details, but it's a big part of the program is to create this beam. And that's the beam, how it looks like, the energy distribution. The big curve is muon neutrinos because they come from pion decays, but there's always, which is important, a small component of electron neutrinos in there. And remember, we want to actually see the appearance of electron neutrinos. So having some electron neutrino component in there is a bit of a problem. And then you choose the type of neutrinos by just flipping the charge of the pions, yeah. Okay, so this is the beam, and so what we should talk about now is the far detector. So the far detector is a time projection chamber. So this is where, so the way this works, you have a big tank of liquid argon. A neutrino interacts, it creates a charged particle. The charged particle ionizes the liquid argon. The ionization flows to you apply a very high voltage, 200 kilovolts order of that, here 170 kilovolts. It drifts over several meters until it reaches a plane of wires which record the charge. You get one coordinate from, so you get information from the drift time it takes. But in order to fully reconstruct here, you have 3 wire planes which are in 3 different angles, which give you then full 3D reconstruction of these tracks. What's so, and this here is the pulses which you measure. So the charge goes, it induces a signal on the first wires and is collected on the third wire. What is fascinating is that you go over about 3 meters, and you drift this, and you can reconstruct the track with a millimeter precision. That's actually quite amazing. Yeah. So there's another technology. So this is called single phase because it consists only of liquid argon. There's another technology called dual phase because it consists of liquid argon and gaseous argon. Now the drift was from the left to the right in the previous picture. In this picture, it is from the bottom to the top. You can see often I've given this talk from the fact that I don't look at the slides anymore. That's if I talk about the wrong slide at some point, tell me. This is so you drift the charge from the bottom to the top. Texting. Okay. So from the bottom to the top, and you do this by applying the voltage in the other dimension. And the advantage is you actually don't have all these stupid wires going around, which is more complicated to build. And then you have an extraction grid here, which is on high voltage. Then you have these large electron multipliers, very thin PCB-style things with holes in them. And that amplifies the charge in the gaseous phase. You read them out on an anode readout plane. You get better signal to noise with this. You don't have to have all these wires, but you have to drift over much longer distances, which is a crucial point. And you are very sensitive to the stability of this plane. So that's some of the challenges of this. Both technologies will be employed in DUNE. And this is basically what I told you. The LEM is here. These are the little holes. They're sub-millimeter holes where the charge gets amplified. Yeah. The anode is then a two-dimensional PCB where you basically read out with millimeter precision. You get the two dimensions. The third dimension is the drift. Yeah. Good. This is fascinating technology because I said you can get like bubble chamber, like for the older generation, the really old generation, I guess. Bubble chambers are still a thing, and you get these images which are like a bubble chamber. And the few caveats about these. This is a real data event from microBoon. Liquid argon is not blue. I know that many people believe this because this is now. This is not a photograph. It's a representation of electronic information. It's very important. It's like a CCD. I mean, you have to reconstruct this. You can't just look at it and say what it is. It still is a fascinating technology. So, did I say everything? Yeah. Just to show how great that is, I like this picture from microBoon, which is a real Michel electron, so that you get the muon from the left decaying. You know how the muon decays. You know, then you have a minimum ionizing particle. I'll show that again in my lectures. It's so beautiful. It's really. Then you get the Bragg peak, where a lot of the charge is deposited at the end. That's shown with a red color. Then it decays into electron, Michel electron, which then is absorbed, and you get some photons. I mean, this is just textbook. Yeah, it's beautiful. Good. So why do we have to go underground? That's because of cosmic rays. Underground, microBoon is this experiment which is running. I'll come back to that. It's on the ground. Every single frame we take in microBoon has 15 cosmics going through. Yeah. If you go 1 mile underground, no cosmics. That's the main reason. You do that in Sanford Underground Research Laboratory. Why does it have the name Sanford? Because there is a very rich guy in South Dakota who gave $70 million to keep the mine pumped dry. Yeah, I think that's a great thing, and he should have his name in there, even if he's not a scientist. I'm I'm totally d'accord with that. So I was there. It's an interesting place. First, what humans do to find gold is just crazy. It's in South Dakota. It's close to Deadwood. You watch Western, you know about Deadwood. It's a huge hole in the ground, which they dug 100 years ago. And you have to move 1 ton of rock to get 3 grams of gold. Anyway, they excavated most of this, and we'll go 1 mile down, which is about half the mine's depth, to build DUNE. This is not the first experiment there, but it will be the largest. There are double beta decay experiments for the same reason, because of background down there, and other experiments, dark matter experiments, and this just shows again the mine. And this is a photograph I took when I was there. These are the different access shafts, and they're actually real. These are not buffalo, these are bisons. Bisons there, yeah? And this you go down, it's actually now being improved in 1 mile in this hoist with this ancient technology, which looks like, you probably don't know what that, like a Doctor Who movie. It is, and you go down this lift like this, and this is the coil with the thing. Now, first year physics question, why does the diameter of the coil increase? Why does it, what? Why does the diameter of the coil increase? I'll be giving lectures next week. You can think about it until then. I think I know the answer, but the problem is also apparent. So what we want to do down there is 4 10-kiloton modules. Each of these 10-kiloton modules is 60 meters long, 20 meters wide, and 20 meters high. This is more than this building. And they are going to be filled, I claim that, I haven't measured it, liquid argon. You have to get all that stuff down in a lift, which is about the size from here to the first row, and yeah, so that's basically, that's going to be difficult, yeah? So there will be 4 caverns, and they are being excavated. Basically, the pre-work started, and they are being excavated properly next year. This is the groundbreaking, with all these important people who have never held a proper shovel in their life. This is a cryostat. This is the outside of the cryostat. How do you build these cryostats? Well, where do you get a cryostat of that size to hold liquefied gas? You get it from those companies that built container ships for liquefied gas, which ship around the globe, yeah? Natural gas. It's the same technology. It's proprietary technology. How to get liquid argon? So, 2,000 lorries. You know what a lorry is? It's a truck, but in England you say lorry. So it's 2,000 trucks of liquid argon which have to go down there. And you actually keep it liquid on the top, gas down, liquid at the bottom. That's a lot of argon. How you get it from the atmosphere, because there's enough argon in the atmosphere. Yeah, that's why it's relatively cheap. So the first detector will follow this single-phase technology, and I'll just quickly go through some of these pictures. So that means you need a cathode and an anode. The anode are the wires. The cathode is where you apply the high voltage. Shown you the animation before. And you do that sandwiched here, so you have an anode plane, a cathode plane, anode plane, cathode plane, anode plane, and that gives the total width. You have an insulation, keep it cold, liquid argon, and then a cryostat around it. The thing is, you have to build per module, you have to build 75 of these anode planes, and this is a lot of work. We are doing, part of them will be done in the UK, part in the US. It's a major construction project over many years to build these. This is how they look like. 6 meter high is the detector, and you see these wires are wrapped in a slightly odd way for a reason which I can explain, but really that important, and that's how the detector will look inside. The wire pitch is about 5 millimeters, yeah? Just to give you a feeling. The second phase is dual phase. This is I showed you. So this is basically dual phase technology, again explained. So this is the second module we want to build, and I've explained that before. The difference is in the cryostat. It looks almost the same, but the dual phase, remember, it goes from the bottom to the top. So it's actually one of the advantages. You can put little chimneys on the top, and you can put the readout through, and you can actually access the thing from the top. This is otherwise is like a space experiment, because once this, for example, the single phase is built and closed, that's it. For the next 20 years, we can't open it. Yeah, so the stuff really has to hold together. Yeah, you have a little more flexibility with this dual phase, but not much. Okay, coming to the physics. We start with a muon neutrino beam. We want to see the appearance of electron neutrino. So we look both for muon neutrino and electron neutrino interactions. The muon neutrino we call disappearance, because we started with muon, so whatever we see left is what is left. It's a bit confusing that it's called disappearance, but anyway, these are the muon neutrinos which are left. The electron neutrinos are the ones that were created due to oscillation. On the left are the muon neutrinos, on the right are the electron neutrinos. There is less appearance than disappearance signal, as expected. This is a simulation with what you can get in 2 times 3.5 years of measurements. Why 2 times 3.5? Because you want to compare neutrinos with antineutrinos. You want to see CP. So you run 3.5 years with neutrinos and 3.5 years with antineutrinos. And this is the signal, and this peak here, this is because of the first and second maximum in oscillation. And okay, this is what you get, and that you fit with the formula we've seen before. That's slightly simplified. You extract delta CP. Yeah. So one problem is, if we look at our detectors, is we have talked about the beam, we have talked about the far detector. We also have a near detector. What do we need a near detector for? Well, the problem is 2 or 3 things. So the near detector we need first because we have to monitor the flux of the neutrinos as they are produced, because our appearance or disappearance signal is always about what happened at the beginning and to the end, so we form ratios, yeah? And so we have to know what was the neutrino flux at the beginning. In order to do that, we have to monitor it, so we have to build a detector to do that right before the neutrinos could oscillate. Secondly, we want to understand the systematics of our detector, and also, you know, how the neutrinos, for example, interact with argon. And that's pretty difficult in the far detector because the rate is actually pretty low. But you can do this in the near detector because you get so many neutrinos, the beam is still very intense, that you can get 100 million interactions in this neutrino interaction. For neutrino physics, that's an unbelievably large number. All what I told you now already basically defines you how the near detector should look like. It should have argon in some form, because you want to study neutrinos on argon. It should have detectors which monitor the beam. And ideally, actually, because the neutrino energy depends on the angle and also for other reasons, you want to be able to move your near detector so it scans the beam at different angles. And actually, all of these things we want to do. In addition, you produce charged particles, so you want to measure those. You want a spectrometer, you want a muon detector, and so on. That's what we are currently designing. That's the near detector, and that is a subgroup in the collaboration that is planning for that. Now, putting all these 3 bits together, then we can actually do a lot of magic. It's actually not, it's statistics, fitting, systematics, hard work, and you extract your sensitivities to the parameters you're interested in. On the left is the mass ordering. It's a particular statistical case because you just want to distinguish 2 cases, mass ordering normal or inverted. On the x-axis is the delta CP parameter, which we don't know. So we have to look at all of this as a function of this delta CP parameter. And on the y-axis is the chi-squared difference between the different hypotheses. So normally particle physicists like 5 sigma as a standard. You can give a whole lecture course on why that makes sense or doesn't make sense. But 5 sigma is kind of the standard. And you can see for all the parameter values, you can actually determine the mass hierarchy with 5 sigma. Delta CP is what we are really interested in, and that is here. So a lot of it goes beyond 5 sigma or 3 sigma in some areas. But then you might say, oh my God, you know what you do here? It's 0. Well, it's 0 because if there is no delta CP, if it is 0, you can discover it. You know, you exclude it. You still make a measurement, by the way. You can make a precise measurement, but you can't positively discover it if you want. That's just fine. Also would be an important statement. As a function of time, it would look like that. So this is a function of years, and you see how the significance for the mass hierarchy and for the delta CP increases with time. There's a little kink in here, and that is because we don't assume that we'll run with 40 kilotons from day one. Yeah, so we slowly stage it. That's what's called staging. And actually what we can do once we discover it, we can do precision measurements like the LHC has first found the Higgs and then done precision measurements. We can do that too. So for example, here delta CP, the interesting one, as a function of time basically here, you see that we can measure with a precision of about 10 degrees, depending on where we are, which is similar to what the precision for these parameters is in the quark sector. And that's very important for the theorists and the model builders. So I'll accelerate a bit, but most of it what I show you are pictures now. This is just the assumption how we'll stage it. I think the main message is physics will start in the middle of the next decade. Just the right time for all the young people in this room. Yeah, you will all be there for you. Beam is very important, and another big part, an expensive part of that project is to upgrade the accelerator at Fermilab. Many countries involved in that. It's called the Proton Improvement Plan. And the idea, you measure this in megawatt, that's just the power of the beam. The more you get, the more the neutrinos, and this is a big technological challenge people are also working on. So let me switch gear a little bit. All of this was about beam neutrinos, but neutrinos come also from other sources, from the sun, atmospheric neutrinos, but also from supernovae. So one thing some people might not realize, and I'm not an astronomer, but when there's a supernova, which we expect in our galaxy roughly every 30 years, 99% of the energy goes into neutrinos. So being able to look at the neutrinos gives you direct access to the working of the supernova. The only information we have from this is from the supernova 1987A, probably before most people's. So, yeah, the few of us remember, yeah. God, this is depressing. So we got 23 from that, roughly, yeah, in 3 detectors. If you do this in DUNE, you'll see, depending how far it is, thousands of neutrinos in a single 10-second burst. Because a supernova takes about 10 seconds, and there's different different phases of the supernova. It starts out with the infall, then there's neutronization, then there's accretion and cooling. So this is like how this supernova goes through different phases. And depending on where you are, you get different flavors of neutrinos. And electron neutrinos dominate here at the beginning because of neutronization, yeah, when protons and electrons merge. And then later, the flux is more flavor symmetric. So by being particularly sensitive to electron neutrinos, which a liquid argon detector is, you can actually monitor this as a function. This is 10 seconds. And you do this with this particular reaction. Why? Because one thing we sometimes forget, the beam neutrinos are GeV. The supernova neutrinos come from the nuclear processes, so they are MeV. So they are like orders of magnitudes between them. So the technology is quite different. They're much lower energy. And you have to look at other reactions, and this is, for example, the reaction you look at here. You can simulate that with a simulation which is called Marley for some reason or the other, and this is a fake, if you want a fake picture, this would be a 17 MeV charge current interaction of a nu E, and it happens somewhere here. And the problem is that all these colors, I'm sorry, but it's not very visible. So the green stuff are neutrons, you can't see those, or very, very difficult. There is some photons, which is in red, and you get energy deposits. Now, if you think, if you ignore all these things which we are cheating and showing you here, there's actually not that much information left, yeah? You only get a few photons around, and that's all you measure. That's quite different from the signals I showed you before. So even though you have thousands of these guys, it will be challenging to reconstruct. One thing you need is good timing resolution, but also very good photon reconstruction. And the way you get that is with a light system. I'll talk about this photon detector later, but this would be the signal you expect in DUNE. This is the energy, this is the time, and you just see the pulse evolving. Now, one thing you could do is Vitor here? You're Vitor, we emailed. So, Vitor, you know, you can explain what the plot shows. You have a poster on it.
Hi, it's working. So I will present this in my poster. This is a neutrino event. This is a time flux event where we can see in the blue line expected event numbers from supernova, disconsidering the oscillations. But if we apply the MSW effects, we can see different scenarios for normal ordering or inverted ordering. So looking at the neutronization burst, we can discriminate if we have inverted or normal hierarchy for neutrinos.
Thank you. And that was not arranged. I mean, it was completely, we didn't plan this. So you can measure what people have been doing for 10 years, how to get the mass ordering in 10 seconds. It's not that easy, but for that you have to read the caveats on Vitor's poster, which we don't talk about right now. But there's some systematic effects, but still it's quite impressive, yeah? So, before I end, let me go through some more technology. Yeah, this exactly. So, first, in order to measure low energy events like supernova, you have to have photons. And to measure photons, there are different technologies. The thing is that liquid argon is a prolific scintillator. There's a scintillation process, which I think next week will be discussed, so we don't have to talk about that with two different light decay times. To get the signal out, you have to first wavelength shift, because it's in the VUV region, so you have to shift it to the visible light. And you have to collect as much light as possible. And in order to do that, there is a scheme which is called Arapuca, which is why is it called Arapuca? Because Arapuca is a bird trap. This is physics nerdy. I knew about the physics Arapuca before I knew about the bird Arapuca. So I'm not sure which one is named after which. So it collects the light, and everybody in Brazil can tell you. It's like carrying coals to Newcastle, which you probably don't know what that means. But that means Newcastle has a lot of coal. So carrying coals to Newcastle means it's like you tell people something which they know much better than you, yeah? So this is a very innovative scheme, and I'm sure Ettore will talk about it next week, to measure light and to trap light through these filters and reconstruct it. I was a bit nervous here, but saying something wrong and then being corrected. So, this is a really challenging technology, building a liquid argon detector, because, okay, there's something called Lariat, and that's a first-generation liquid argon TPC at Fermilab, and has been running for a few years. And you can see it, and Lariat is about this size, okay? Like a fish tank. We want to build one which is 60 meter long and 20 meter wide, 6 meters high, yeah? 12 meters high. So it's actually quite a challenging thing. So you have to build intermediate steps. And we do this with the proto-dunes. They are built at CERN on the Neutrino platform, both 6 times 6 times 6 meters, basically like one sub-block of the detector, and one for single phase, one for dual phase. This is the CERN North area, which was built extra for that, extended extra for this effect, for this measurement, and these are the two cryostats, and this is, I always get the direction wrong, I think we are looking at this is where the beam comes from. Oh no, this is the dual phase and this is the single phase. I'll just claim that and it doesn't matter. And there'll be charged particles beam pointing towards it, which there are no neutrinos there. It will use cosmics and charged particle beam to demonstrate the technology. There's also a smaller prototype called 3x1x1 for the dual phase technology, and just shows you again these beautiful tracks here. There was a publication, if you're interested, which shows it. So I had the privilege to go inside the dual phase and single phase detectors. Some photos I took. So this is the dual phase from the inside. It's a cryostat. There's not much in there. I mean, it's like being in a big tank. What you see here is the high voltage cage. There's a high voltage cage which creates the high voltage, and which is you see the slices because this separates the how do you say, the high voltage is being, it's like a resistor chain, yeah? And so the high voltage is applied there, but otherwise it's like an empty, a very beautiful, awe-inspiring place in there. High voltage is a really critical thing here, because that's one of the problems. You have to keep that high voltage stable. And we have actually managed to keep 150 kilovolts, just remember it's 600 in the final detector, stable in vacuum just recently. So that's a big success. For the single phase, we have these huge APAs. You remember these wire planes? This is one of the wire planes which we actually built in the UK. Others were built in the US. And they are tested in a cold box here, because you don't want to test them in your detector, because then you get them out if they don't work is really hard. So you built a little detector, a little box where you cool it down with, usually use nitrogen, not argon, because it's cheaper. And you test all the electronics and things like that. And what you want to measure there? Well, if you have, one of the things, you have to get the noise as low as possible. Noise is your enemy, yeah? Because it prevents you from measuring small signals. And you see that on the next plot. So this is what we did here. This is the noise measured in some arbitrary units, this number of electrons. And here you see that for the detector, you have the cooling, this is time, this is about 20 hours, something, 2 days. And you cool it down and your noise goes down, and it's about a factor 2 below what we wanted. Works perfectly. So this is just some indication that this detector technology really, really works. So the schedule for this proto-DUNE detector is very ambitious, and why that is, I'll say in a moment. Currently, the single phase is closed, and liquid argon will be filled in within days. It starts, first it gets purged with gas, and then it fills with liquid argon. That takes a week or so. Then the detector will be turned on. The dual phase is still a little bit behind, but hopefully will be ready in about 2 months. Then there will be a beam, which is due to the LHC shutdown, there will be availability of beam, and we put charged particles in, and we can use these charged particles to actually calibrate the response of the detector. But we can also do this with, normally the cosmics are a problem when you don't want them in your detector as background, but here they're actually good because you can use them to calibrate your detector, yeah? Okay, and why? Because next year we want to come out with what's called the technical design report, which basically puts all in a very long document and says that's what we want to build. The other type of liquid argon detectors, which are the same size, which are currently being built, are the short baseline neutrino program at Fermilab. And just for completeness, and because I'm on microphone, I wanted to add this. This is Fermilab, and these are 3 liquid argon detectors that measure neutrino interactions very close to the beam to look for things like sterile neutrinos. And these are also of the similar size as Proto-DUNE, about 100 tons. That's the microboon detector as it is lowered down. This is the cryostat where the liquid argon is. Why did I want to mention this? Because these detectors are extremely important to not only show the technology works. Proto-DUNE is actually closer to DUNE, so it's actually more important in that sense, but also to get the software and understand these interactions. And I show you end with 2 pictures. This is data. This is a neutrino interaction in microboon. And this is where the neutrino came in. This is a pion, this is a muon, a cosmic, and cosmic. These are beautiful pictures. And now you would think, oh my God, that must be really simple to measure, to reconstruct that, yeah? Because I look at it and I know what it is. And unfortunately, it is too much information, TMI. It is really, really hard to write these algorithms. You know, it's like the famous cat and dog problem on the internet. Now, there are algorithms which the internet uses to distinguish faces, for example. These are convolutional neural networks and stuff like that. So one thing on microboon we have done is look at, okay, you can do this in the old-fashioned way, which is still very good. You know, you take a hit and you take the next hit and the next hit and you spit them together. Or you just say, well, a pion is a cat and a muon is a dog. Can you distinguish this with a convolutional neural network? And you actually can. This is a pion and a muon. I have to peek now which one. The top is the muon. Well, how can you tell? Because of the kink at the end, yeah? And then there's the pion also because it's shorter. And you run a convolutional neural network, and this is actually Monte Carlo. It's a bit cheating, but anyway. So this is how it classifies these. That's pretty good. But it also, there's an enormous amount of software behind this, and you know, real complicated stuff people can do, and you know, student projects, which is also technology which, you know, in the real world, the non-science world, you know, that's what these are capabilities if you know how to do these kind of things, which are really important. So the last slide, what's the timeline for DUNE? So the timeline, we are here. We have the Proto-DUNEs. 2019, there's the technical design report. 2019, the physical excavation of the site down here begins. First module installation in 2022. And 2026, we have neutrino beams with 2 far detectors. This looks like a long time, but if you have been around for a while and you know how projects work, this is, I've never seen anything as aggressive than that. Proto-DUNE 2 years ago was all on paper. It works now. It's amazing how fast that goes. Quite an impressive thing, which was only possible because it is an international project where many people contribute, including many very creative and important physicists from Brazil. Thank you.
Thank you very much. Do we have questions?
I have 2 questions which are very different, but one is, what's the cost of this experiment as compared with other big science experiments?
Yeah, okay. Of course, costing something is always difficult, but I just put out a number, $1 to $2 billion.
What would CERN be, just to compare with something like that?
CERN has a yearly budget of 1 billion Swiss francs, which is $1. So 1 Swiss franc a dollar is almost the same. So CERN's budget is about $1 billion a year. So it's about two years. Now, one has to be careful because with all labs, we all know that the overall budget of any institution and what you can use for research is a huge difference, because you first have to pay for the electricity and you have to pay for all the other people who do work, and so what you have as a research contribution is not the full 100%. Yeah, but that's roughly the scale of what we are talking about. Now it's divided over many countries. I mean, the US pay bulk, but just to give you a scale, the UK contribution is of the order of $100 million.
The other question is, you talked about some theoretical models at the beginning. Do these theoretical models say anything about the parameters that will be measured, or will you be able to rule out something like the seesaw or something like that?
Andre?
So I'd like about theoretical models. Yeah, do they say anything about this parameter space?
Yeah. So you want to take that one? I
can say something.
I can.
Yeah. So this is a complicated question, and there are many, many models that try to make statements about the values of mixing parameters, for example. So those models you can clearly test. There are models that have something to do with how neutrino masses happen, and these models very seldom will have some characteristics that will leave an imprint in a neutrino oscillation experiments, but they don't have to. So there are many, many models of the neutrino mass generation that are not tested by oscillation experiments. Some of them are. And then you have all these flavor models which have something to say about the parameters themselves. And then of course you have the looking for new phenomenon aspects of DUNE, which of course Stefan didn't concentrate on, but that's another big deal, is to see if we actually understand everything about neutrinos in a way that's consistent with all the precision data that they'll have. And we hope that something will not work, and that we actually learn something that guides us in a certain direction.
Yeah. I mean, one way to look at it is if you look at the flavor at the mixing matrix in the quark sector and in the neutrino sector, you see they have certain characteristics. The quark sector is very diagonal. The lepton sector is not diagonal. They are all over the place. And you can come, you can try to look for symmetries, for example. And there are theories that start from certain symmetries and then predict based on these symmetries how these matrices should look like, for example. Yeah. Thank you. Well, we base all our initial sensitivities, as I showed one plot, on 7 years, but we expect, I mean, realistically, similar to LHC experiments, I expect this to run over 2 decades with a, and that depends then also very much on what is being seen and, if what is, similar to the LHC, the extensions beyond some point, 10, 15 years are not guaranteed, obviously, yeah? The famous, yeah, once every, because it's 30 years, but unfortunately it doesn't, 1987 plus 30, we better speed up a little bit. Yeah, actually, it might be close, yeah. But this is Poisson statistics, and so we'll, yeah. I'm not on the supernova part of things, but God, imagine it comes like 3 months before. No, I can't even think about it. But then you look at LIGO, how lucky they were. They.
I would say how lucky Virgo was. So I have a related question on the supernovae neutrinos, even though it's not your field. But suppose there is a supernovae during the DUNE's lifetime, which is already a little bit lucky. So what is DUNE capable of doing that other experiments around the world would not be? I mean, can you compare? I mean, what we learn with DUNE regarding supernova neutrinos that we don't learn with Kamiokande or whatever is running at the time?
The particular strength of DUNE is the sensitivity to electron neutrinos. So, and you saw the shape of the electron. This is different from a water Cherenkov. It doesn't have the same sensitivity. So you actually can, for example, one thing you can do, which is very important for the models, is to and a good timing resolution to with sufficient statistics reconstruct the pulse shape you get, which tells you, when we say, I talked about the mass hierarchy, but there are different models about supernova explosions out there which predict quite a different structure of these pulses as a function of time. Not with the same, not in the same way, no.
Any more questions?
Also, you want always we want multi, we don't want to have one detector. I mean, ideally, I'm all for a water Cherenkov neutrino detector. I have no problem with that. The more the merrier. And this is not one against the other. Of course, there are other things. You could even look for diffuse neutrino background from supernova. I mean, this is not what I picked. Is just a few flagship topics. Yeah. Where the other experiments are better, like water, is directional information. Yeah, there'll be very little directional, if any, in these. Yeah.
All right, I don't see more questions, so I think we can thank our speaker again. And please join us for refreshments upstairs. Thank you.
Good. Good. You liked it? Good.
Very clear, very informative.
So I'll take that out and give you the. Is this the data stick?
So for those on the school,
Oh.
we can have 5 minutes of refreshment for those of the school if you wanna know. But we'll have our coffee break later. So let's be back here in 5 minutes, okay? For the school, those on the school, and we'll take the picture.
Thank you. Thanks for coming. No, this doesn't work. This is not the right.